so many people are coming here because this is the really last session of today. So thank you for coming. Here's the topic of my presentation. Let's start. I'm working for Netmarble. So you may not know about Netmarble. A brief introduction to Netmarble is a Korean game company which is developing mobile games and publishing. As for 2017, Netmarble ranked number 3 in global mobile publishers after Tencent and NetEase. We began using Ceph storage in production environment from 2016, replacing storage that could have a critical impact on game services with Ceph was big challenges for us. Fortunately, we have been operating Ceph stable until now, so we are expanding Ceph storage for other purposes. Now we have total 8 clusters of Ceph storage. About 4 petabytes of data is stored on the cluster. In detail, there are 3 clusters that are used for KRBD block storage. And there are 4 clusters that are used for Cinder backend block storage. A lot of game services are running on the OpenStack environment. We have one object storage cluster as an archiving storage service, which is the biggest capacity have. We are planning to utilize object storage a lot in various environments. Data processing storage will be implemented for data lake of big data system. Also, origin CDN storage will be implemented soon using Ceph object storage. Today, I'm gonna analyze the default features of Cinder works in the Ceph-like snapshot backup. Moreover, I will also analyze the complex Cinder feature like image cached volume, Cinder replication that are applied due to reduce the impact for storage failure. At first, let me introduce myself briefly. My name is Haan. From 2011 to 2016, I used to work at Samsung SDS developing cloud platform, especially OpenStack project. From 2016, I've been working for Netmarble. Since working at Netmarble, I'm responsible for the overall strategy, planning, and operation of Ceph storage. There has been a lot of work replacing storage with Ceph in many areas, but there is still much more to do, and I'm very grateful to learn so much through this Cephalocon. Let's start with basic features. There are 3 topics in the default Cinder features. Most of all, I should explain what is Cinder for people who is unfamiliar with the Cinder project. Cinder is a block storage service for OpenStack. It provides storage resources to end user. Ceph is the most popular choice for Cinder backend driver as shown in the table below. The link tells how to integrate Ceph as a Cinder backend very kindly, so I'm gonna skip this. This is part of the process of integration with OpenStack and Ceph. Each OpenStack project uses RBD types of the pool for data store or backend driver. The name of each pool is defined in the configuration file. Also, the RBD pools should exist in Ceph cluster by creating the pools in Ceph side. You can find those pools in Ceph df command after creating each pools. Pools are the logical group for storing Rados objects. These pools are made up of placement groups, and the Rados object will be stored in the placement group. The placement group containing Rados objects are spread across multiple OSDs in order to improve reliability. Let's look at how Ceph actually works when we create a specific size of Cinder volume. We create a Cinder volume which has unique UID name. Cinder user can configure the Rados object size, which Ceph divides the volumes into. RVD volume, which has the same name of volume created in the Ceph side. If we configure RVD chunk size to 4 MB, the RVD volumes will be divided into 4 MB Rados object. 8 MB object are also same as 4 MB. Then let's find where the real data of the Cinder volume is stored in the Ceph storage. There is a Cinder volume created by user. The volume is divided into Rados object of the same size. In Ceph, actually, RVD volumes will be created in Ceph volumes pool. The RVD volume divided into 4 MB size of Rados objects. The names of all Rados objects in the RVD volume start with RVD under the data and unique ID. In Ceph, actually, RVD volumes will be created in Ceph volumes pool. The RVD volume divided into 4 MB size of Rados objects. The names of all Rados objects in the RVD volumes. We can find and list of all Rados objects belonging to the RVD volume because they have same name prefix. These objects are distributed in each placement group. Crush algorithm computes the placement group for each object. A placement group aggregates objects within a pool because tracking object placement and object metadata on a per object basis is computationally expensive. With the Ceph OSD map, we can find which placement group the object is stored in and which OSD the placement group is distributed in. In this case, the object is located in 77.500 placement group, and the placement group is distributed in the 345, 323, 264 OSDs. The object's contents within a placement group are stored in a set of OSDs. Basically, default value of replica is 3, so each placement group will store objects on 3 OSDs. Connect to one of the OSD nodes identified in the OSD map and access to OSD data directory. A directory is created with the name of the placement group to which the Rados object belongs. If you access the head directory, you can see that the Rados object data you selected is actually stored. In the case of BlueStore, the process of OSD map is the same as that of FileStore. But it is difficult to find actual Rados data because placement group is not created as a directory like project format. In BlueStore, there is a way to find objects like project format. Using Ceph Object Store tool to mount it in one directory, you can see where the actual data is stored. Ceph is basically copy and write operation where it is integrated with OpenStack. Read-only snapshot is created from the original image and cloned image is created from this snapshot image. Legacy storage has similar concept, but the differences between legacy storage and Ceph is that Ceph provides the image data store of glance service. Therefore, the instance does not need to copy through network, make it fast when provisioning instance with Cinder volume. You must set show image direct URL configuration to true in glance in order to use copy and write. All cloned volumes have relationship with the glance images. Let's check through the RBD command. The same name of the UUID of glance image created in images pool, and the image snapshot will be created subsequently. After that, this snapshot is set to protected in order to use read-only image. And a lot of Cinder volumes are created that cloned from the protected snapshot image. These cloned volumes are actually connected instances and used as a root volume. If you type RBD status command, you could find that the compute node where the instance is running on. Contents of default XML of instance as RBD volumes path. Next is the snapshot feature of Cinder and Ceph. I'm going to explain the snapshot of Cinder first. As you know, snapshot is captures of what a volume like at a particular moment in time. Cinder snapshot can be restored into a general Cinder volume or transferred into a Cinder backup volume. The differences between volume restore and volume backup transferring is restored volume use RBD clone function, and backup transferring is that the real data transferred from snapshot to Cinder backup volume. Cinder snapshot feature utilizes the Ceph snapshot function. The Ceph snapshot concept is exactly the same as that of Cinder. User can choose whether flatten or not when creating volume from snapshot image by setting RBD flatten volume from snapshot key in configuration file. This is identical to the result of running the RBD flatten command on the Ceph actually. Now let's look at how Cinder snapshot works on actual Ceph. Here is a snapshot by Cinder command. In Ceph, you can also see that the RBD snapshot with snapshot dash before the same name was created as the corresponding snapshot. If we set RBD flatten volume from snapshot to false, restored volume from Cinder snapshot will be cloned from the snapshot, which has relationship with the original Cinder volume. As you can see, there is a parent volume is specified in the restored volume information in Ceph. If you set to true for RBD flatten configuration, restored volume will be completely independent of the parent volume. Cinder provides a backup feature in addition to snapshot to preserve the data of the original volume. Several storage can be used as backend of Cinder backup feature. Ceph uses the RBD export diff and import diff functions to perform Cinder backup operation. There are two types of Cinder backup that are full and incremental backup. Full backup and incremental backup perform a little differently. In case of full backup, snapshot is created from Cinder volume and RBD volume will be created in backup pool. After that, the snapshot of the Cinder volume export and import into backup pool. In case of incremental backup, full backup must be exist before. then import the differences to the backup volume in comparison to the snapshot of the originally created Cinder volume. After importing the data in this way, the snapshot of the Cinder volume created for its incremental backup will be deleted. Let me explain how the volume backup feature provided by Cinder actually works in Ceph. Here is the command to create a backup volume via Cinder. The backup create command will create a full backup by default if no other options are given. RBD volume image will be created in backup pool in the Ceph side. And then you can find a snapshot volume named backup that blah blah of the backup volume is created via export diff, import diff function. We can add incremental option in order to create incremental backup volume in Cinder. In fact, with the Ceph volume backend, you can't choose whether you want a full or an incremental backup. It's automatic. If the origin volume is stored on a Ceph backend, then the backup will be incremental if a full backup is already exists, and full if this is the first backup of the volume. Now you can see two incremental backups in this screenshot. This is the command for creating incremental backup volume through Ceph. This command combines export and import command with stdin and stdout. RBD export diff command creates simple binary file that stores some information like original snapshot name and the snapshot name, size of the image at ending snapshot, and the diff between snapshots. Import diff command will write the contents of the difference to the backup image and create a snapshot with the same name as the origin ending snapshot. Here are two incremental snapshot images existing in this method. We can have a periodic backup polish for critical data like database with this functionality. What I have described so far is the basic features of the Cinder with the Ceph backend. I'm going to explain features that are the result of our efforts to storage failover. We have experienced many failures using legacy storage prior to Ceph. We are always concerned about this storage failure even we operate our cloud infrastructure with Ceph storage. The most concerned part was Ceph's copy and write method utilized in Cinder. Here is a list of children volumes from a specific glance image volume. As you know, a read request for data of cloned volumes get from base image and write data into cloned volume. At this time, if the data of base image is corrupted, it can be affected to all cloned volumes. Usually, it created incredibly many instances with a small number of base OS image. So if such problem occurs, the impact will be great. So we have been finding solution to minimize these effects. We've decided to use image volume cache feature in Cinder. Image volume cache features improve the performance of creating a volume from an image by eliminating network copy process. When creating instances with volumes, Cinder internally creates a cached volume and for the next generate instances. The instance provisioning speed via cached volume is greatly increased. For using the feature, we should set several configurations in Cinder.conf file. The image volume cache requires that the internal tenant be configured for the block storage services. This project will own the cached image volume actually. If Cinder with Ceph backend applies the image volume cached feature, it will work as following picture. The volume of the first instance created from the base image is flattened from the parent volume and created as an independent volume. A protected snapshot will be created from these volumes. Subsequent instances that are requested to be created from the base images are created as child volumes of the volume snapshot. Even if you delete the first instance, Ceph actually does not delete this volume, but keeps the name at .delete end of the name. By applying the actual image cache volume in Cinder, you can see lots of image cached volumes having names start with image dash. The cached volume is separately created for tenant, glance image type, and Cinder volume size. In other words, the base image type in which the root volume of the instance is cloned becomes a distributed structure compared to the copy on write. This greatly reduces the impact of the base image corruption. Let's see how Ceph provides the image cached volume features. Actually, there's no specific features for achieving image cached volume in Ceph storage. Here's the volume from an instance initially created. It is flattened when after cloning from the base OS image. Then protected snapshot created subsequently. Actually, this volume is already deleted from Cinder. That is why that deleted string is added at the end of the name of volume in this screenshot. Here is cached volume, which is cloned from the protected snapshot. The root volume of the instance created after that will be created by referring to this volume. Another concern with storage operations was the failure of the entire Ceph cluster, which is related to DRR storage. Cinder provides volume replication since Juno release. This functionality is for disaster recovery. So we applied the dual functionality to prepare for the failure of the whole Ceph cluster. Let me explain Cinder replication in detail. Replication feature of Cinder is dependent on the backend driver's implementation. There is no automatic failover since the use case is disaster recovery, and it must be done manually when the primary backend is out. Here is overall step for Ceph replication in Cinder. The Cinder replication of Ceph backend requires two different Ceph clusters. Configure Ceph clusters to mirror mode and apply mirror to pool used in Cinder. In most cases, use the volumes pool. Copy the configuration file and key of each Ceph clusters to the Cinder volume node. Then add the replication setting to the Ceph backend of the Cinder configuration file. In case of using Ceph as a Cinder backend, Cinder utilizes RBD mirroring functionality. RBD images can be synchronously mirrored between two Ceph clusters. This capability uses the RBD journaling image feature. From the dual release, Ceph started supporting the RBD mirroring feature. These are two types of mirroring. When applied to pool unit, all images created in the pool are mirrored automatically. or can be configured in image unit only. You should install Ceph mirror package in order to use the feature and running a Ceph RBD mirror process. RBD mirror pull peer add command is used to peer the different clusters. At this time, since the peer is established based on the host node, the information of the different clusters is registered in the host file. Here we can see how the volume is created in the actual Ceph clusters. You can see that a journaling feature has been added to the volumes in all Ceph clusters. The mirror status shows up plus start in the primary cluster and up plus replaying in the second cluster. This is how failover is processed in Cinder. You can find that the replication status of Ceph backend service is enabled before we do failover process. If you have a problem with primary cluster, we can let Cinder do failover with the failover host command. The replication status failover is changed to failing over after we did. This is the result of failover process. A normal volume that has not been created with the replicated type will be an error state. And the replicated type volume will fail over and can use normally. If you look at the actual Ceph cluster, you can see that the mirror status of the two clusters have changed each other. So we are continuing our effort to make Ceph storage suitable for our environment. Sometimes our architecture has other side effects. Sometimes it has an inefficient structure. However, such a lot of trial led our team to understand more about Ceph. Thank you very much for coming. And is anybody have a question?